Hey guys, Dr. Brown here, and tonight we're trying to answer a question that a high schooler asked just recently who's being introduced to calculus for the first time, or pre-calculus in their case. The question is, what is a derivative? So let's get after it. All right, you know from your algebra days that if you have a function, let's say, well, if we started with a dry marker, how about that? We have a function y versus x here, and you have something that looks like that, okay? Well, that's a straight line, correct? Okay, what do we know about that? Y equals mx plus b. B is my y-intercept where x equals 0. So it's that point. Okay, my x-intercept is where y equals 0. I could be that point. But what's the slope of that line? Well, in this equation, that's what m is. M is the slope, and we know m equals the change in y over the change in x. Now for this particular function, I could say this is my change in x, and that's the change in y. This could be my y sub 2, y sub 1, and this could be x sub 2, x sub 1. So I know y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's the slope. Now in calculus, we talk about a derivative. Now back, I guess the late 1600s, they're trying to figure out how you determine a tangent point on a curve. So let's say I have some curve, it looks like that. How do I establish then a tangent point on that curve? And that became the source of a lot of evaluation, and they finally determined if I have a secant line, it's really about, if I have a secant line, let's say I have a line that cuts it at those 2 points. It's really about finding the slope of the secant line. Now that's not secant in terms of trigonometric functions, but just a Latin term, I think, for meaning to cut. So it said if I let this line get shorter and shorter, let's say I want to know the slope at that point. If this line is shorter, say it goes from here to here, and then it goes from here to here, and then from here to here, what's the slope at that point of that secant line as it gets closer and closer to the point? So they're really trying to do this very thing, okay? But keep it really small. So let's think about that. Let's redraw. Now we're trying to find m, because m, the change in y over change in x, as it gets, that change becomes really small, that's what a derivative is. Okay, so let's redraw our curve. Let's say it looks like that. Let's redraw our secant line. We're going from here to here, and we're trying to understand the slope of that line. Okay, so I have some value of x, and then I have f of x. That's my y value. Y equals f of x. Okay, so what is this one? Let's say that this change in x is h. So I'm increasing it by h. So this point right here is x plus h. Okay. The y value would be f of x plus h. So what does that look like in terms of my slope? Now my slope, dy dx, derivative of y with respect to x, is the slope from a calculus perspective. See, so now it's not just m anymore, but it's dy dx. It lets me know still the change in y over change in x. So what is that? Y sub 2 is f of x plus h minus y sub 1, which was f of x, over x sub 2, which was x plus h, minus x sub 1, which was x. So let's see, f of x plus h minus f of x divided by x minus x is 0, just leaves me with h. So that is, actually that's still m. I should have left that up here. That's still m. But in terms of calculus, recall what I said earlier, is h becomes smaller and smaller and smaller. That's what a derivative is at that point. So let me do this. Let me take the limit as h approaches 0 of that function. So that's f prime of x, or dy dx. There's a lot of different ways to write that. It's the limit of that function as h becomes smaller and smaller and smaller. So you may be thinking, well, big wooey, what does that mean for me? Okay, let's get ourselves some space here. Let's assume that, like this function here, y equals x squared. And we want to find the derivative of x squared. Okay, so what does that mean? I'm going to take the limit as h approaches 0 of x squared. I'm going to take x plus h squared minus f of x. Well, so f of x equals y equals x squared. So minus x squared all over h. So now let's FOIL this. We would have the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Now I should have defined what a limit was for you high schoolers. I mean, limit as h approaches 0, it just says I'm going to look at this thing as x gets closer and closer and closer and closer to 0. Now you'll notice h can't equal 0 right now because it's undefined. I can't just say, oh, 0, undefined. No, let's not do that. Okay, all right, so x squared minus x squared, those cancel. So I have the limit as h approaches 0 of 2xh plus h squared, that's what's remaining, over h. When in doubt, factor, okay? So I have the limit as h approaches 0, I'm going to factor an h out. H times 2x plus h divided by h. H divided by h is 1, so those cancel out. So now I have the limit is h approaches 0. What do I have left? 2x plus h. Hey. Okay, as h approaches 0, now I can let it be 0. Well, that just wipes out, so that equals 2x. So the derivative of x squared, the rate of change of x squared with or f of x being x squared is 2x. There's power in that. And you'll find out what that means over time. Okay, now I'm going to link another video in and dealing with the 9 rules of differentiation. And I would encourage you to learn those. You'll absolutely need those. Now, for example, if I have y versus x, so y and x, and I have that line right there. It's a straight horizontal line. What is the derivative or what is the slope of that function. Let's say this is 2, for example. Y equals 2. Y equals 2. So f of x equals y equals 2. What's the rate of change of that? Well, let me pick a point here, pick a point here. So I have x sub 2, x sub 1, y sub 2, y sub 1. So my slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And y is 2. It's a horizontal line. 2 minus 2 over x sub 2 minus x sub 1. 2 minus 2 is 0. Now I could, if this were calculus were working, dy dx, the rate of change of y with respect to x of a constant is 0. The slope of a constant is 0. Okay? All right, so that's one rule that's important. Now then, what if we show you another rule that's called the general power rule? Let's say y equals x squared, same as before. The general power rule says, well, I'm going to say dy dx, the derivative of y with respect to x is, I have this x squared, I'm going to take that 2, bring it down here. And then I'm going to subtract 1 from that. So that gives me 2, bring the 2 down, x to the 2 minus 1, which is x to the first power, which is just 2x. So there's a power rule that allows us, instead of taking the limit of all of these things, we can get to that derivative quicker. Now you may be thinking, well, why do I need any of that? Oh, what's the derivative of sine x? So y equals sine x. Can I use the general power rule with that? No. I have to plug that in here and work through it. Okay? So yes. Okay, I think you can hear me now. All right, so there's, obviously you'd have to put in sine of x plus h minus sine of x all over h, and there's a certain trigonometric rule for sine of two angles, okay? And so I'll leave that one with you. You can work through that. But that's why you have the limiting functions, because there are certain items out there you can't solve any other way. All right, so hopefully this makes a little bit more clear what a derivative is for you high schoolers out there. It's the slope at a point. All right, that's all for now, and you guys keep studying. Why are we doing this? Together we're trying to build a better tomorrow and do that through math. Okay, keep studying. That's all for now. We'll talk to you next time. Thanks.